All right. Welcome today. Thinking, normally I just taught my C class, so I know exactly what lecture number it is. I think we're at lecture number 20 right now of assembly language class. We got a little bit of leftover material from last time. I think that's going to work out okay because I think the regular lecture material for today is going to end up being a little bit short. So you'll remember last time we were trying to, as quickly as possible, cover as much as we could of the ARM instruction set. It's a good example of a RISC instruction set. It's probably about the third RISC assembly language that I've programmed in, just since I've been writing a little bit of code in assembly language. And like all RISC instruction sets, it is very cleverly designed. They figure out how to get by with a more limited set of instructions and addressing modes and things like that. I think this is what we were covering at the end, and we already covered some of this. We talked about how we're going to use ARMSim as a software platform for simulating the ARM instruction set. You may have access to a machine that runs ARM, but most of us probably don't, and even if you did, you wouldn't have, depending upon your OS, you might not be able to make the same system calls we count on using. So we're going to be using ARMSim. I played with this a little bit since we met last week, and it looks like we're going to need to use a slightly older version of ARMSim rather than the one that's the most recent version. I've been updating some of our materials for that, but I haven't posted them to our website, but I'll try to start doing that this evening with some new instructions for how to install ARM and hopefully get it working, or ARMSim. We talked about this last time. Mostly this involved talking about, well, if you're using ARMSim, then just like the raising various interrupts on the 8086, we can generate software generated interrupts to get the operating system to do things for us. And here we're going to count on reading and writing files. And I think we covered all of this, how to prepare the CPU registers with what file you want to open, what you can get back with each of these system calls. So we talked about opening a file, closing a file, reading a line of text from a file, and writing a string to a file. And we got as far as this, but we didn't talk any about data declarations. Any questions before we kind of resume about halfway through this deck of slides? All right, these you'll find pretty familiar. Same idea as what we've been doing with MASM on the 8086. We can reserve space for variables for data, and the syntax is pretty similar. There's a label, and you can think of that just like a label in your instructions that marks where the next data item is. Here we have a colon at the end of the label, so the same syntax as we've done with labels within our assembly language. And then the next item is, well, you can use that to declare word, half word, or byte-sized data. Or if you just want to skip a number of bytes, you can do that to reserve space that you don't want to initialize yet. So you can think of this .skip as leaving, well, it leaves a 4-byte gap between the V1 label and the next label, which we're going to put in on the next slide. So you can think of that as reserving 4 bytes of space, the size of a word on ARM, but one that we don't need initialized to a particular value. If you want to initialize your data items, you can initialize them as words. And this is showing some examples of that. So .word says reserve me 1 or more words of data. And then you can initialize them with, well, a decimal integer like we're doing here with a value of 1,000. Or you can give a value in hexadecimal. Instead of putting an H at the end, we've got a more C-like syntax with the 0x in front. So this is a hexadecimal constant. So this words V3, this word size piece of storage will start out with this value in it. I said a moment ago, you can reserve half words. So when you say, if you say .h word, you're reserving 2 bytes of storage. You can initialize these the same way. And just like we could in 8086 or in MASM, you can treat these as signed or unsigned values. And it's up to you, the assembly language programmer, to remember how you're storing each item. For initialization, if you give a positive value, then it doesn't really matter if it's signed or unsigned. If you give a negative value, then it's going to store it as a 2's complement negative value. And since and you remember 2's complement values, the size of the data item matters. So a -10 that's byte sized is going to be different from a -10 that's half word or word sized. So here, since we know this is a byte we're setting aside, it'll store a -10, essentially sign extending it all the way to a byte in width. What else might we want to do? We probably want to be able to reserve characters and strings. And there are two ways of doing this. With .ascii, ASCII, it reserves just the sequence of characters you ask for without putting a null terminator at the end. With ASCII-Z, you can think of that Z as meaning 0 terminate this, or mark the end with a null like you normally would a string in C. So this reserves, this V7 is going to reserve a 3-character string plus 1 more byte at the end that it'll store a null terminator in. So this .ascii-Z is kind of analogous to how strings get reserved in the C programming language. Remember, we talked about this when we were talking about the software interrupts. There's no $sign end of string marker like we had in DOS. For the ARM programming we're going to do, it's going to use a null termination by convention to mark the end of strings.
Does this mean that we can't do the thing we were doing in 8086 where you can just say, okay, I want to reserve a byte and then reserve like 6 bytes, 6 things that are all.
Oh, with the dupe?
Yeah, well, like you could mark out a list of like, you could say byte and then 6, 12, whatever, and it would. Am I misremembering that? Am I going?
No, I think you're remembering it right. Yeah, there's no examples of that, but I feel like I've seen one. It's just not on the slide. I think you can still put multiple constants. You wouldn't be able to do that with skip, but with byte, I think you could say 10, 5, whatever. I'm going from my half memory that you can do that. We've got 3 sample programs, so I'm trying to segue to say, we could check and see if any of the samples offer this. We've got 3 sample programs that come with the ARM assignment, and I haven't done it yet, but I'm gonna go ahead and post these individually on our website so you don't have to unpack the archive to get them and take a look at them. One reason for that is I've noticed that the case sensitivity of ARMSim looks like it varies by platform. So if I'm running on a Windows machine and I try to get it to open hello.s, it's fine if it's capital or lowercase. On Windows, it'll open either. But when I do it on a Linux machine, it wants a lowercase .s at the end. The archive has all of these in capital letters, so it means you have to rename them to get them to open, at least by default in ARMSim. So I'm going to rename them myself and just post them. And one reason I go ahead and mention that is that'll give some examples of the stuff that we're talking about that'll be easy to take a look at. I haven't posted those yet, but if you look at our website, there's a section about ARM kind of down near the bottom. I'll go ahead and add these 3 examples to that, so you ought to be able to just click on them and look at them. These are, I think we had these same examples back when we started doing 8086 assembly. An example that just prints out hello world, mostly, oh, and when I say prints out, I mean it writes it to a file. So it opens the file, writes out the hello world string, and then after it's run, you can see that the file exists and that it'll have hello world in it. There's a copy string that reads a string from a file and writes it out. And there's also a copy file that'll read, I think, the entire contents of a file and write it out to an output file. So these will give some examples of data declarations, of ARM instruction sets, and backing up several slides, this stuff. the software interrupts that we talked about really at the tail end of last lecture. It's still several weeks away, but you have an ARM assignment that you get to do. It's worth less than most of the other programming assignments. And some of that's because it'll probably be pretty easy. For the ARM program, you get to redo at least a version of what we did back on our first programming assignment when we were writing the key program, except instead of reading from the keyboard, instead of reading from the user, it'll read from a file. And instead of using dot to terminate the program, we'll just, I think we just, yeah, we read up until the end of the input string, the end of a line of input. So we're gonna, so it'll be a lot like the key assignment, except no special treatment of dot. We'll read in the dot character, we'll just ignore it. We won't even print it out. I know it's been a while since you did the key assignment, but remember that was the one where you read in characters. For uppercase letters, you print them out as regularly. For lowercase, you capitalize them and print them out. For spaces, you just print them out as spaces, and anything else, you read it in and ignore it. And this is the one change for this version of the assignment, or this is one of the changes. You'll be reading in dot, but just ignoring it. It won't terminate the program. And instead of reading from the keyboard, you'll be reading from a file, and you'll be printing output to a file. First thing you'll want to do is get ARMSim installed on your system, and I've updated the installation instructions. Like I said, you don't want to install the latest version of ARMSim. I think the latest version is 2.01. It looks like version 1.91 works much better for the example programs we have. For instance, it looks like they changed the comment character, and they changed the way software interrupts invoke system calls. So we'll rewind and use an older version of that. But then a lot of this will be similar. You'll want to think about a design for your solution. You'll want to code it up. And then you'll be able to test and debug this and then grade it using a grading program, much like we've done on the previous assignments. And then you'll submit the output from the grading program. You'll remember for the 8086 version of this, this was probably the first time you had to spend a little bit of time thinking about reducing your instruction count. And some of you might have used the translate instruction, the one that lets you build a big table that says what to do and what to print out on each input character. ARM doesn't have an instruction like that. At least it doesn't have a dedicated instruction that does a table lookup. But by now we've learned a bunch of indirect addressing modes, and we could build, if you wanted to, you could build something that worked like the translate instruction yourself by having one register. Remember, there's this addressing mode. Let me point to it, this one right here, that has two registers inside square brackets. And that just adds the values of the two registers and then gets the contents of memory there. So you could use this to have one register pointing to the start of a table, and then the other could be an index into the table. And then with a load instruction like this, you could kind of simulate the translate instruction if you wanted to do it like that. I've got this assignment posted, but I need to update it just like I've done with the other assignments. I need to sneak in and change the point value for it and do some other things to update it for this semester. The version that's posted should be enough to let you get started working on it if you want, but I'll go ahead and try to update it so it matches what we're doing this semester a little bit better. Questions before I try to move on? All right. That was stuff we were supposed to cover at the tail end of lecture last time, so it's kind of leftovers. For today, we're starting a little bit of a 2-lecture series about microcode. Today, we'll talk about what it is a little bit, and we've got a couple of examples of instructions that typically might depend on microcoding as the way they're implemented in hardware. And then I think next time next time will be a week from today after our exam. We've got an example of microcoding that we'll work through in a little bit of detail. We've talked about this kind of thing before, sort of a disagreement in design philosophy. The complex instruction set model, where we believe it's okay to design a CPU with a bunch of different instructions and indexing modes that do a bunch of often specialized things, versus the RISC model, which says your processor should have, in a way, as small an instruction set as possible. And all of those instructions should be as uniform as possible. When I say as uniform as possible, I mean things like they should have the same encoding length. They should run in about the same execution time, or in the same number of clock ticks. And we've seen examples of each of these. The CISC model, you can see from the range of dates there, that was more popular up until the 90s. And RISC has been more popular, at least has gained a lot of popularity since. But both of these still end up being viable ways of trying to design a processor, and they have some advantages and disadvantages. I started to say, and we've seen an example of each of these. The 8086 processor would be a good example of a CISC instruction set, a CISC model, whereas ARM, that we spent a little bit of time on, is more typical of a RISC design. In the early days of microprocessor design, it was easy to believe we could just, or maybe it was a good idea to just put more and more functionality right into the hardware. So if the hardware could do an instruction faster than you could do it with software, why not just build as much as you need, as much as you can, into the processor? And like I already said, this yielded processors where there were maybe a bunch of different addressing modes, a bunch of different ways of accessing your data, a bunch of different types of instructions, including some that were very special purpose, that handled data in special representations. I remember it used to be able to get a processor that would do what's called binary coded decimal, where they would take a hexadecimal number, but they'd use it to store just 2 decimal digits rather than storing something in binary or storing something in hexadecimal. So specialized data formats like that, we've seen with 8086. If you've got a bunch of specialized instructions and addressing modes, it's easy to have instructions that are different lengths depending upon what kind of data they need to use, and that might have varied execution time. Some instructions might run in a single clock tick, some of them might take longer to run. Whereas the RISC model tries to simplify things a lot, especially getting rid of a lot of special purpose instructions, and trying to go with a small set of instructions that are at least enough to do, to implement whatever you might want to do in a higher level language. This is based on the observation that a lot of those special purpose instructions that might have been built right into a CISC processor sometimes didn't get used that much in practice. And if they didn't get used that much, then they're kind of wasting space on the microprocessor. They're kind of wasting power whenever that microprocessor is running, if it's got big sections of the processor that maybe it's not using. So some of the complexity of the design of a CISC processor and some of those specific instructions might have been just, or the argument might be, they were just wasting space on the microprocessor. So you saw this with the ARM processor. A RISC design might favor just a few addressing modes, just some simple ways to access memory, and an instruction set that includes as few operations as you can get by with, usually implemented with instructions that are all the same time and that all run at the same execution speed. And last time we saw some of why this matters. We talked about the pipelined design of a ARM processor, and it's easy to run a pipeline if the fetch, decode, and execute stages all take the same amount of time. If every other instruction is taking vastly different times to execute, then your pipeline is not going to do you as much good. So on a RISC model, we're going to get, I've said it a couple of times, we're going to try to get by with as few instructions as we can design. And by having fewer instructions that the processor needs to support, maybe it can do a better job of implementing those instructions more efficiently. And I already said this a couple of slides ago. You probably don't need to be told. The 8086 is typical of a CISC design, and ARM that we just learned about is typical of a RISC design. This is warming up a little bit for the idea of how a CISC design implements a lot of different special purpose addressing modes and instructions. So how do you build a microprocessor and build in a lot of special purpose instructions, a lot of special purpose addressing modes? And it's right there at the top of the slide. This has often been done with microcode. We mentioned this a few weeks ago, but we didn't have time to talk about it much then. We're going to spend a little bit more time on it today. Microcode is a sequence of low-level instructions built right into the processor. You can think of it as, like it says on the slide, kind of sub-instructions that make up the machine instructions that we've been learning about. This may seem weird because we've already been learning instructions that seem like they're very low level. But if you think about it, the instructions we might describe like the loop instruction, even in describing that instruction, we kind of had set steps that we would describe. It would be things like, well, take the value in CX and decrement it. And then check to see if it's 0. And if it's not 0, go jump to a particular label. So it's kind of like in implementing that instruction, there are a couple of steps that you have to do. And there are other instructions where to do what that instruction says might naturally be implemented as a sequence of steps. Take some of our addressing modes that we've talked about. You might have an addressing mode that says something like, take the value of the BX register and add the value of the DI register. Then go get an immediate constant and add that in. And then go get whatever's in memory at that location. Well, just implementing that addressing mode is something that seems like it could take multiple steps. Those steps are the kinds of things that could be implemented with microcode. Your processor might have some capabilities of doing things like adding 2 numbers or going and getting something at a particular memory location. And using low-level instructions built right into the processor, you could design multiple machine instructions, multiple assembly language instructions that are implemented by running hopefully a short sequence of these microcode machine instructions. You could kind of compare this to a subroutine call in a regular higher level programming language. If you call a subroutine like square root, it's kind of understood that to compute a square root requires a few steps. So when you call square root, it goes and jumps to a subroutine and runs the sequence of steps it takes to compute a square root. Well, what we're saying with microcode is we could, inside the processor, implement machine instructions, or at least certain machine instructions, that way. If you had a machine instruction like a multiply, and that's what we're showing over here on the right, one that might take multiple steps to do, you could implement that by a sequence of very low-level machine instructions, microcode instructions, that do the various steps it takes to do a multiply. And we'll work through an example of that, and I'll try and convince you, yeah, you could implement multiply that way. Now, these are low-level machine instructions that are not available even to the assembly language programmer. So these are what internally might implement assembly language instructions, at least on a CISC model. You don't get to program in these instructions. And any given machine language instruction that you're accustomed to using could be implemented by one or more of these micro instructions, ones that are hidden within the processor. Why would you want to do it this way? It gives you more flexibility in your design. You could say, well, if my processor has certain capabilities, like it could add two 16-bit numbers, or if you tell it if it knows the address, it can go get a byte out of memory at that address. And then the particular instructions it can do are coded using microcode. Then that could give you a flexible way of implementing a microprocessor that could do a variety of different instructions. You could even change your mind. You could take the same basic hardware and change the microcode to get it to run different types of instructions, or to add support for additional instructions. And since adding more instructions just requires writing a little bit of microcode for each of those, it would make it easier to extend the instruction set. You just have to have space for storing those additional implementations of instructions in microcode. That last item says this could have some advantage in terms of performance. But you'll notice also performance shows up as a cost. So implementing, and I want to argue for that. So implementing instructions in microcode could have some performance benefits, but it could also hurt performance. Let's talk about how it could hurt performance first, because that seems like the more obvious thing. If every machine instruction that you run requires you to go run a little sequence of microcode instructions, then that seems like more overhead to running that instruction. If, say, an add or a multiply requires going and running a little subroutine in microcode, then going and looking up that subroutine and then implementing, or sorry, running, doing all the little microcode instructions could have, that's a lot of steps. That could have a lot of overhead compared to just building a circuit to do that instruction. So that could hurt performance, but I guess a place where it could help performance is with microcode. You could build instructions that do a lot of things all in one instruction. And if that's an instruction that gets used a lot, maybe being able to call one machine instruction and have it do a big task like the loop instruction, maybe that could give us overall faster machine language code by packing more functionality into individual instructions. So that could be a benefit, but it's also going to be a cost if you end up having to run a lot of little machine instructions, each of which requires going and running a little bit of microcode. Also, and we definitely saw this with 8086, if you've got a bunch of different instructions, each of them using different types of data and different addressing modes, your instruction set is probably going to be non-uniform. Instructions are going to vary in size, they're going to vary in execution time, and that's going to make it harder to do things like fetch instructions in advance and do things like pipeline your instructions. So I've tried to do I've tried to do a job of describing what microcode is. We've got some examples that'll try to help illustrate this. Questions before I try to move on? So the CISC model, microcode, was a popular way of designing a processor that was flexible and that could support a large number of varied and often special purpose instructions. To see two different design philosophies, let's talk about an operation like a multiply operation. And to make it easier to talk about, we're going to look at a tiny little example of a multiplier. Its job is going to be to multiply two 2-bit numbers. So over here, A0 and A1, those are 2 bits of input for one of the numbers. So A0, kind of like it's written down here, A0 we're going to pretend is the low bit of one of the numbers we're multiplying, and A1 is the other bit, the higher bit. Same thing with B. B0 is the low bit of the other multiplicand, and B1 is the high bit. And then just like we saw with registers on the 8086, these two 2-bit numbers are going to multiply to give us a 4-bit product. This circuit shows how you could implement this in hardware. I don't think we've seen this in this class yet, and I don't know if you get to see this in the computer science curriculum, but these are called gates. They implement the logic operations that we've talked about in higher level languages, operations like and or, and exclusive or, and not. And the way we're wiring these together show how you could build a circuit that uses those basic logical operations to compute something. And we'll talk about what this circuit does, what it computes, and we'll work through an example. Here, we'll kind of pick the biggest example we could do if you've built a 2-bit multiplier. So it multiplies a 2-bit number by another 2-bit number and gives you a 4-bit number. Then this is the biggest input we could give it. In binary, that's a 3 times another 3. So we put 1 in each of the inputs for A and a 1 in each of the inputs for B. And this is, at least looking ahead, this is the output we should get from this circuit. This is just one test case, but we can talk about what this circuit would do on this input. These green gates are AND gates. They compute the AND operation, the same bitwise AND that you used in C class or that we've used in this class, except here they each just have 1 bit of input. So this one right here, for instance, is an AND gate. One of its inputs is B1, so the high order bit of B, and tracing back, it looks like its other input is A1, the high order bit of A. This end is its output. Its output doesn't go straight to one of the output bits, but it gets used as input to a couple of other gates. All of these green ones are ANDs. So if this circuit works, it looks like we're using 6 AND gates to implement a multiplier. And these kind of reddish ones, that's a notation for an exclusive OR gate. So it works just like the exclusive OR operation that we've talked about. This one here takes inputs that are the result of a couple of these AND gates, and its output is the exclusive OR of its 2 inputs. So if, I'll say this real fast, if both of its inputs are 0 or both of its inputs are 1, then the output is 0. If exactly one of its inputs is 1 and the other one is 0, then its output is 1, just like the exclusive OR operation. So for the example we were playing with, if we're multiplying 3 times 3, then all of the inputs to those AND gates, and you can trace them back, but they all come from these A and B inputs. So all of those inputs are going to be 1. And since those are AND gates, well, if any AND gate has both of its input as 1, its outputs are also going to be 1. So all of the AND gates, all of that sort of first column of gates are going to have 1 as their output. This gives us enough to see at least one bit of our output, C0, according to this figure. It just depends on the output of this AND gate. So we know it's going to be a 1. The rest of these depend on the other gates. But now that we know all of these outputs are 1, we can go ahead and start thinking about the gates that depend on those. This AND gate has 2, now it's going to have 2 inputs of 1, so its output is going to be 1. This exclusive OR gate has 2 inputs that are 1, so its output is going to be 0. So now we know 2 bits of our outputs. Continuing, we already said, yeah, the output of this AND gate is going to be 1, and we already said the output of this AND gate is going to be 1. If we trace this back, all of the inputs of these gates, well, this one is the output of this, and we just said it was 1, and then all the, well, this one input also is a copy of the output of this. And then I'm trying to quickly say, well, where did this 1 come from? It's the output of this, and we already said that was 1. So again, all of the inputs of these 2 gates are 1. So for this gate, since it's an AND gate, its output is going to be a 0. And this top one, since its inputs are both 1, its output, sorry, I said that wrong. But let's do the one that the slide just showed. So since the inputs of this gate are both 1, it's an exclusive OR, so its output's going to be 0. The bottom one, its inputs are both 1. And I think I said this wrong a moment ago. So its output is going to be a 1. So if we look at the bits of the output, sure enough, reading from low to high, it's 1, 0, 0, 1. And we already said that's what we should get as output. If you want to confirm that, you can just look at each of these in decimal. And yeah, in binary, that's a binary for a 3 in decimal. Same here, that's a 3, and that's a 9 in decimal. And 3 times 3 should be 9. So at least it looks like in this one case, this circuit does the right thing. We could check the other cases. It seems like there'd be 16 different possible inputs for this circuit, and we could check all of them. And if we wanted to build a system that could multiply numbers pretty quickly, we could build this into hardware. It would take a bigger circuit. How efficient would this be? Well, the time to execute depends on the depth of the circuit. So when this AND gate, for instance, gets its 2 inputs, there's a moment before you can depend on its output to have the AND of its 2 inputs. So that's propagation delay through that gate. Well, all of these gates are going to execute, or at least are going to get their inputs at about the same time. So their outputs will be generated at about the same time. And then the input for the next layer of gates will be available. And then the input for the next layer of gates will be available. So the execution time really depends on how long it takes the result of this computation to propagate through the, well, in this case, the 3 layers of gates we have in the circuit. So the execution time is dependent upon the depth of the circuit. Now we just saw, what does it take to build this? Well, this is a small multiplier. It multiplies 2 2-bit numbers, and it cost us 8 bits to do that. This wasn't too bad. Even if we had to come up with this on our own, we could, especially, now that we know how the gates, what they do, and that we could implement a multiplier with this, with gates like this, we could probably figure it out ourselves. If we had to build this in hardware for a bigger multiplier, we could probably do it, but it would take a much bigger circuit. But then once we built that, it would be able to very efficiently compute the product of, for instance, if we did this for 2 16-bit numbers, then it could compute any 16-bit product. That would give us a faster way to multiply it, but it would take an awful lot of gates. And that's kind of the point that we're making down here. To multiply these 2 2-bit numbers, that already took 8 gates. It's going to take a lot bigger of a circuit to multiply 2 16-bit numbers. thousands of gates to do that. When the 8086 processor came out, it had 29,000 processors, and we can't afford to spend them all on multipliers. So an easier way to do multiplication was to implement it in microcode, to do a multiply not with a dedicated circuit that does multiplication, but by executing a sequence of steps right on the microprocessor. And at the time, on the 8086, multiplying two 16-bit numbers might have taken between 118 and 133 clock ticks to do that. Dividing was even more expensive, between 144 and 162 clock cycles to do a 32-bit divided by 8-bit division. This is one place where you've seen performance improve a lot over the generations of microprocessors. Years later, when the Pentium processor came out, it was a much bigger design with around 42 million transistors. And a lot of that circuitry was spent doing things like this multiply operation faster. On this, with more dedicated hardware for basic operations like this, the cost of a multiply was down to 11 cycles for a 16 by 16 multiply. For the same division operation, down from around 150 cycles to around 25 cycles. Backing up to the 8086, we said, well, one reason the multiply was so comparatively slow is they did it with a series of steps. What does it take to do that? That's what I wanted to talk about next. Questions before I try to talk about kind of our one biggish example of how you could do this with microcode. All right, if you had to do a multiply and you couldn't afford to spend just a huge amount of real estate on your processor just to implement multiply, you could do it with a sequence of cheaper operations, in particular, shifting and adding. And microcode could implement really a little program on the processor that did multiply this way. And that's what we're going to show here and on the next few slides. Let's pretend you want to multiply A up here. So in this example, it's 3. Same example we were doing before, just we got some extra, we're pretending we have some extra high order bits. A multiplied by B, and we're going to do it not by a dedicated multiplication circuit, but by doing a bunch of shifts and adds. We're going to do this for every bit of B. And N is going to be our counter of which bit we're looking at right now. So it's going to start out at 0. And that's going to be kind of saying, well, we're looking at at the low order bit of B. And then we're going to look at the next bit and the next bit and the next bit. So B is going to tell us when to do an add operation. A is the value that we're going to add in. But in every iteration of this operation, we're going to shift it to the left. So initially, and this down here is pseudocode for what the microcode might do. So I won't point to this a whole lot, but as I'm talking through this, I'm kind of doing what this little program says. So first we look at the low order bit of B. It's a 1. That says to add in a copy of A. You could think of this as, well, in binary, that's like the 1's place. And if you're multiplying B times A, well, if you got a 1 in the 1's place, then that's like saying I want 1 copy of what's in A. So I'll add that in. And, sorry, I probably didn't say this. C is our product. So down here, as we do this algorithm, C is going to accumulate the product of A and B. All right, so first step, low order bit of B says add in a copy of A. So I add that into C, and now C is just a copy of what's in A. And then looking at B, well, I've just looked at the ones place. I've got a bunch of high order bits, including this one in the next bit position. That one says you need 2 copies. Well, if you think of this as a binary number, that one's worth 1, that one's worth 2. So if you're thinking of this as saying, well, you need 3 copies of A added in, you can think of that one as saying, well, this is the ones place, so you need 1 copy of A. That's the twos place, so you need 1 copy of 2 times A. Well, I'll do the 2 times A by shifting A to the left. And I just did that between the previous slide and this one. Backing up, we had just added a copy of A into C. Then I'm going to shift A to the left, effectively doubling it, because now I'm going to look at the next bit of B. Every time I move to the next bit of B, I'm going to increment my counter n. So n's going to go up to 1. And the next bit of B is going to say, oh, there was a 1 in B, there was a 1 in the twos place, in the next binary digit. So why don't you take another copy of A, of shifted A, shifted, so now it's worth twice as much, and add that into the product that you're accumulating. And when I add that in, we could do the binary addition. 0 plus 1 is 0, 1 plus 1 is, sorry, said that wrong. 0 plus 1 is 1. 1 plus 1 is 0 with a carry into the next bit. That carry of 1 plus 1 is 0 with a carry into the next bit. And then that carry of 1 plus 2 zeros is a 1. I didn't really have to do that because it's right on my next slide. So because there's a 1 here in the next bit of B, we add in a shifted copy of A, and we continue. So we got to do this for 2 more bits. We shift A to the left. My picture doesn't show this, but as we continue, A would get shifted again, but then we're not going to do anything with it because the next bit of B is 0. And then for the next iteration, we're going to shift A to the left again, but we're not going to add that in because the next bit of B is 0. So when we're done, we only ended up adding in the copy of A as it was originally because of this low order bit. And then A shifted to the left by 1 bit because of this bit. And that gives us 1001, which is what we were expecting to get. Same problem we had before. So this is essentially 3 times 3, and it should give us 9. And sure enough, that's what we got in binary. So this is a way of implementing multiply, but instead of having one dedicated circuit that does it, where the cost of the multiply is dependent on the depth of that circuit, here it's dependent on the number of bits in B and whatever the cost of your add operation is. We got another example. We'll go through this real fast, or we'll try to, because it's the same algorithm. We've just changed the numbers. So now B is 111, so that's 7 in binary. And A, we're pretending, is just 0010 or 2 in binary. Same thing as before. So this is A. There's a 1 in the low order bit of B. So we add a copy of A into our product. So C looks like that. Then we shift A to the left. We look at the next bit of B, and it's also a 1. So we add in the shifted copy of A. And I've tried to make the point, every time you shift A, you're doubling its value. So we're adding in twice what A originally was, effectively saying, oh, because this 1 here is really worth 2, because it's in the 2's place. And then we continue, we shift A to the left once more. We look at the next bit of B, and it's a 1, so we add that in. We don't have a slide for it, but then to continue the algorithm, we would shift A 1 more time, but then we wouldn't have to do anything with it because the next bit would be a 0. So we'd be left with 1110. which is 14, which is what we should get. If we rewind back to before we started shifting stuff around, we were computing 7 times 2, and we got 1110, which is 14, which is what we should get for 7 times 2. So this is a way to implement multiply in a way that doesn't require a whole lot of logic circuitry. You need to do a shift operation, but that's easy to implement in hardware, and you need to do an add operation, but we've already figured out how to implement an add. That doesn't require the kind of complexity that a multiply requires. It's just doing it this way could require quite a few steps. This is the thing that we just did. This is just explaining it mathematically. So every time we took A and shifted it to the left, we got twice, or we were doubling the value of A, and then we added that in whenever the corresponding bit of B was 1. So that was our somewhat protracted example of how a lot of more sophisticated operations that the processor could support could be done with the help of microcode, limited or less sophisticated logic hardware, but more steps and even a tiny little internal language in the form of microcode for describing what those steps were. We said this before, that an advantage of microcode would be it'd be easier to add new instructions, even to change the instruction set supported by what was otherwise the same hardware. IBM did this in around the 1960s. They had a processor, at least the logic of a processor, that could run a particular instruction set, but with different or additional microcode, you could change the instruction set it was able to run, but just by changing the assembly language instructions that it recognized and writing microcode to implement those various instructions. We've made the point that there's a bit of a performance trade-off since microcode means every one of your instructions, or at least many of your instructions, might involve going and running a little program to do what that instruction is supposed to do. That could make a lot of your instructions slower unless, or sorry, I'll say that would make a lot of your instructions slower, but it could pay off if you had some instructions that did a bunch of things all within a single instruction, some complex instructions that could replace lots of individual machine instructions. And that's what they tried to do. In fact, if you look at the 8086 instruction set, you'll see what are called string instructions, where an individual instruction can copy or compare or search for things in a whole sequence of memory locations. And that's what we're going to talk about next. These are kind of like the multiply instructions. They're implemented with the help of microcode, and any one of these instructions could be like running a little program from a single assembly language instruction. They have names like move S, and that's for copying. The S part is for moving a string, but it wouldn't really have to be a string, at least not a string like we think of it in C. It could be any sequence of bytes. So move a chunk of memory, and that B at the end is for byte. So I'm going to copy a sequence of bytes from one region of memory to another region of memory, all in one machine instruction. There are a couple of ways, if that's all you wanted to do, there are a couple of ways you could do it. You could write this yourself using a bunch of machine instructions. And if you did it, this is the kind of program you might write, even in assembly language. So let's pretend you had 80 bytes of memory. And let's say you wanted to copy it from one chunk of memory to another. And let's pretend these were in your data section. So A is the label for the start of the place you want to copy from. So you want to copy 80 bytes starting from label A. So pretend that's some variable, that's some location in your data segment. And you want to copy those 80 bytes to another place in your data segment starting at B. So if you had to do this yourself, you could say that's a good job for the SI and DI registers. The names even help to remember what you're doing. Remember, SI is for source index and DI is for for destination index. So I'll just load the starting address of each of those regions of memory into those two registers. And I'll use C to keep up with how many bytes I'm copying. So it'll start out at 80, and then every time I copy a byte, I'll decrement it. So this is kind of my setup. And then using as simple a sequence of instructions as I can, I'll just write some machine code to copy it. So I'll go get a byte of memory that SI points to. I'll copy it into the low part of the AX register. I say it's a byte because if you're copying to AL, then you're only copying a byte. And then I'll turn around and copy that byte into wherever DI points to, into the destination block. I just copied a byte, so I'll bump these two pointers ahead. I'll use the inc instruction to move them ahead. And then I'm using CX to count how many. I'm going to copy 80 bytes. So every time around, I'll decrement CX. And as long as it doesn't hit 0, then I've still got more to copy. So as long as it's not equal to 0, as long as it hasn't reached 0, I'll go back to the top of the loop and copy the next byte. So every time around this loop, this copies a byte from source to destination. And it's going to take 80 iterations of this loop to copy the whole thing. What if I told you one of those instructions that we just learned about, one of those string instructions, could do all of this? And that's really what the string instructions are made for doing. This move instruction that we just talked about, move string, is designed to do what we're doing here. In fact, it doesn't even need operands. It is made to copy from whatever the source index is pointing to whatever the destination index is pointing to. Those are each assumed to be in, well, I'm going to say in different segments. I think the source index, I think is coming from the data segment. And I think the destination index is going to the extra segment. You could always make those segment registers point to the same place, and then you could easily copy within the same segment. Or you could have them pointing different places to copy from one region of memory to another. So this instruction is made to copy from what SI is pointing to what DI is pointing to. And every time it copies a byte. So it does this first, these two instructions, or at least it replaces them. It does what they do. And then every time it copies a byte, it automatically bumps those two registers forward. So on each execution, it also does these increments. And it automatically, kind of like the loop instruction, it automatically uses CX to keep up with how many times it's going to do the copy. Actually, I misspoke a little bit there. That's really the job of this rep in front. So the move SB copies one byte from SI to DI and bumps them both forward. And this rep modifier in front says, don't just do that once, but do that a number of times given by the CX register. So this rep in front replaces kind of these last two parts. It says decrement CX every time and keep doing it until CX reaches 0. So this one instruction can copy, well, in this case, 80 bytes from a source to a destination, or as many bytes as you need to copy, as long as CX has enough capacity for that. So we're really, well, if we look over here, we had 6 machine instructions that did this, and we're replacing them all by 1 machine instruction. So the job of fetching and decoding each of these instructions with this one CISC instruction, it's going to be a lot cheaper. In fact, it's more than that, because each of these had to be fetched and decoded 80 times. Whereas with this instruction over here, we fetch and decode it once, and then it still has to access memory 80 times. But while it's doing that, the processor isn't having to go fetch the next instruction, and then the next instruction, and then the next instruction. It's already got its instruction. It's just running the various steps of copying those bytes all in microcode. So this is one way you can think about it. The microcode steps to do this instruction are kind of like what we're doing over here. It's just they built all of that behavior into this one move instruction with the rep modifier in front. And you can kind of compare the costs over here. We got 6 instructions that we each have to fetch 80 times. Whereas over here, we still have to access memory 80 times, but we're just running 1 instruction while we do that. And this would be a case where CISC, this one CISC instruction, could be a lot faster than doing all of this yourself. If you let me back up a bunch of slides, I said, well, there might be places where you could find this in part of the built-in stuff in your language. You may remember from C class, there was a mem copy instruction, or not an instruction, it was a standard library call that was made for copying one chunk of memory to another. And this could be a reason to favor using something like memcopy rather than doing that yourself in a loop, because you don't know how memcopy is implemented, but whoever implemented it probably knew to take advantage of machine instructions like this. And on a system that might have a special purpose instruction for copying big blocks of memory, letting a single instruction do that could be better than what you could get, even if the compiler tried to write optimized code for doing this copy. That gets us caught up. We started a lecture today a little bit behind, but that's all the new stuff we were hoping to cover. I'll hang around if there are questions. Any questions here at the end of today's lecture? I'll go ahead and stop screen sharing so I can see how many people are here. Looks like we still have a few people. Any questions before we call it a day?
I just wanted to ask whether we're still having class on Wednesday. I didn't catch if we did or not.
We have, so the exam is replacing class, kind of like if we were meeting in person. I haven't sent out the week's announcements yet, but I'll make sure to put that in probably Tuesday morning's announcements. We won't meet on Wednesday. We'll pretend the exam replaces that.
Gotcha. Thank you very much.
No problem. Other questions? I'll go ahead and stop recording.